Okay, let's look at another example. Now, instead of a 1D elastic collision, let's look at an inelastic collision. And this is a little more complicated problem that's sort of similar actually to the question that we looked at in the in-person lab. So the ballistic pendulum. So it kind of has two stages to it. So we'll analyze it in a similar fashion. So the question says, a 930 kilogram sports car collides into the rear of a 3,000 kilogram SUV stopped at a red light. The bumpers lock, the brakes locked, and the two cars skid forward 2.8 meters before stopping. Police officer, estimating the coefficient of kinetic friction between tires and road to be 0.8, calculates the speed of the car at impact. What is the speed? Okay, so let's kind of sketch this out before we jump into trying to solve it. We have a sports car. Oh, it's a sports car. Let me make it more pointy. And what we're actually looking for is its initial speed, so we don't know what it is. But we do know that it has a mass of 930 kilograms. Now let me put this somewhere else here. And we know that it is going to collide into an SUV, which has a larger mass. Ah, what a terrible drawing. So let's call this one B. It has a mass of 3,000 kilograms, and we also know that its initial velocity is going to be 0. And what's going to happen is these are going to, crunch together. And then there's going to be some friction between the road and the vehicles, and they are going to, skid forward some distance before coming to rest. And okay. So what else do we know? We know we're going to kind of break this into stages. So this is sort of the first situation before they collide, after they collide but before they've moved, and after they've come to rest. So what all do we know? We know that this is going to be a completely inelastic collision. They stick together. So if it's inelastic, we know that momentum will still be conserved, but energy will not. So we'll be able to use basically momentum conservation to figure out the speed of the combination of vehicles. And then what we'll do is we'll use energy conservation in the presence of a non-conservative force, so friction, to calculate, to connect the kinetic energy of the combination of vehicles to the work that's been done by friction. So here we'll use energy conservation with friction, or in light of friction. So that kind of gives us the setup and the game plan for our approach. And this was coefficient of friction we'll need to make use of to figure that out. And as you can see, it's sort of similar to what we did with the ballistic pendulum, where we looked at momentum conservation, and then we looked at an energy argument. So, okay, let's start with the momentum conservation piece. So we know that the momentum at 1 is going to have to equal the momentum at 2. So what will that look like? It'll be MA VA is going to have to be equal to MA plus MB times why don't we call this velocity of the combination VA plus B? So in other words, after they've collided together, we're going to be calling their speed VA plus B. And let's call this equation 1. So this is the first thing that we know. So then let's look at the energy conservation piece. So for this, we have friction present. And so let's just be really kind of complete about it, and then we'll note that a bunch of these will be 0. So we have been talking about the potential and kinetic energy. So the sum of the potential and kinetic at 2 is going to have to equal the potential and kinetic and work that's been done by non-conservative forces. So in this case, friction. And we'll note that potential energy is not an issue in this situation because there's no change in height. So these will all be 0. And we would also note that the kinetic energy final is also going to be 0 because V final is 0. So really, we're left with a pretty concise relationship here, just that the kinetic energy at 2 is going to have to be equal to the work that's been done by friction to bring it to a stop. And we can be a little more explicit here. Let me make this a tiny bit smaller so we have some room. Let's put in what the kinetic energy is. So 1/2 m A plus B. Well, here, let me do like this. So the kinetic energy is going to have to be equal to the work done by friction. What is work done by friction? So recall, work done by friction is going to be the force of friction times the distance. And the force of friction is mu times the normal force. And the normal force in this situation is just going to be the weight of the combination. So in other words, this work done by friction would be mu times ma plus mb times g, i.e. the weight of the combination, times the distance. So the force of friction times the distance. So we can put those ingredients together. And notice the mass appears on both sides, so we can cancel that. And we could solve this then for the velocity of the combination. So we would multiply by a factor of 2, mu g d, and then we would take a square root. Okay, so now we have an expression for the velocity of the combination. And notice we have in equation 1 something that relates the velocity of the combination to the initial velocity of the car. So let's combine those ingredients together. So let's call this equation 2. If we substitute equation 2 into 1, we have ma VA is equal to ma plus mb times our velocity expression. And notice we can divide by a factor of ma on both sides. Cancel that, and we're left with an expression for VA, the initial velocity of the car, that depends solely on the masses of the vehicles, the coefficient of friction, gravity, and the distance. And we can put in those numerical values. Let's put in our numbers here. So this will equal 930 plus 3,000 times the square root of 2, 0.8, 9.8, 2.8. We multiply that stuff together and crunch our numbers. We find that this is 28 meters per second. And in a car, that's about 62 miles per hour, which is fast, but definitely a reasonable speed for a vehicle. So this question, I think, is good. It's a little more complicated. Gives us a chance to practice both with an inelastic collision, but also sort of a multi-stage problem. So one of the things I think that you'll find as you get further in your physics is that you're going to be combining ideas together. So work from friction was way, work we looked at in chapter 7. Friction was all the way back in chapter 5. Energy conservation in chapter 8. And now momentum conservation in chapter 9. This problem is a cool opportunity to kind of combine those different ideas together. And as you get farther, you're going to have to develop your skills in figuring out which concepts you need to apply in which situations. So hopefully this problem helps you solve similar problems that you see in the homework.